Good evening, everyone. I'm Anu Gayatri.
Good evening, madam.
Good evening, ma'am.
Myself and Varsha will be. Thank you. Myself and Varsha will be co-hosting this 6-day online faculty development program on deep learning and computer vision in clinical research. So we are currently in our 4th year of MSc Data Science program at Tyagaraja College of Engineering. We look forward to an engaging and insightful session. It is with great enthusiasm that I welcome you all to this Atal online faculty development program on deep learning and computer vision in the field of clinical research. This 6-day event will serve as a platform of researchers over to Asha. Before we advance into the session, we shall have the prayer song followed by Kalai Thandai Vazhuthu. रमाहण्डहारं श्रुतिव्रातसारं जडान्तर्विहारं तरापारहारं सितानन्दरूपं मनोहरस्वरूपं त्रितानेकरूपं भजेगं சித்தத்துள் சிவத்தை வைத்தார் செந்தமிழ் நாவில் வைத்தார் வித்தகம் தொழிலில் வைத்தார் விருப்பினை தொண்டில் வைத்தார் எத்திசை புகழும் வைத்தார் எண்ணிலார் வாழ வைத்தார் அத்தனாம் தியாகராசர் அன்னலை கருத்துள் வைப்பார்.
Thank you, Anu. On behalf of Tyagaraja College of Engineering and the coordinators, Dr. T. Chandrakumar Sir, Dr. M. S. Sasirekha Ma'am, Professor R. Saraswati Meena Ma'am, we are pleased to welcome our respected Principal, Dr. L. Ashok Kumar Sir, our respected Head of the Department of Applied Mathematics and Computational Science, Dr. S. Parthasarathy Sir, and our Honorable Chief Guest, Dr. Sushmita Mitra Ma'am. We are truly privileged to have renowned resource persons from esteemed institutions and industries with us today. Their expertise in AI, deep learning, and medical data analysis will provide us with invaluable insights into this rapidly evolving field. We also extend our gratitude to the internal faculty members, research scholars, and technical staff for their continuous support and dedication in organizing this FDP. Your efforts have been instrumental in making this program a success. Lastly, a special welcome to all our enthusiastic participants. Your presence here reflects a shared passion for advancing AI applications in healthcare and medical imaging. We look forward to an engaging, interactive, and insightful learning experience over the course of this FDP.
To officially inaugurate this faculty development program, I now invite Dr. S. Parthasarathy Sir, Head of Department of Applied Mathematics and Computational Science, to deliver the welcome address.
Good evening to all of you. On behalf of the Department of Applied Mathematics and Computational Science of Tyagaraja College of Engineering, Madurai, I have great pleasure in welcoming the chief guest for this inaugural function, Professor Sushmita Mitra, Full Professor Machine Intelligence Unit of Indian Statistical Institute, Kolkata. Welcome you, ma'am. I have great pleasure in welcoming all the external participants, internal faculty members, PhD scholars, and student friends, and the members of organizing committee of this AICTE online Atal 6-day faculty development program on deep learning and computer vision in the field of clinical research. I am sure that The participants will make the best use of this opportunity provided by the AICTE through our department. We have identified the best resource persons for all the 6-day schedule, and you might have received the different topics that would be handled by the external experts during this 6 days training program. I welcome you all once again. Thank you.
Thank you, sir. Now I request to honor. So, to inaugurate this FTP, we are honored to have Dr. Shushmita Mitra ma'am, professor at the Machine Learning Unit, Indian Statistical Institute, Kolkata. She is globally recognized expert in machine learning, soft computing, bioinformatics, and medical image processing with over 30 years of research experience. She has authored seminal books such as Neurofuzzy Pattern Recognition and Data Mining, Multimedia Soft Computing, and Bioinformatics. A recipient of multiple prestigious awards, including the J.C. Bose National Fellowship, IEEE TNN Outstanding Paper Award, and Fulbright Nehru Senior Research Fellowship. Dr. Mitra ma'am has specifically contributed to AI-driven disease diagnostics and bioinformatics applications. She is a fellow of IEEE, the World Academy of Sciences, INSA, IAPR, AAIA, IASC, and INAE, and NASI India, and serves as an associate editor for multiple high-impact journals. With over 150 international research publications, her expertise has shaped the field of data science, deep learning, and medical AI applications. She has held visiting professor positions at University of Alberta, Meiji University, and Aalborg University, further solidifying her influence in the field of AI. Please join me in welcoming Dr. Mitra ma'am, who will deliver the inaugural address followed by the keynote talk on the role of AI in clinical research.
Thank you so much. So do I have to talk now or later?
Yes, ma'am.
Okay, so the inaugural address. Okay, thank you so much for having invited me, Dr. Parthasarathi. I'm very honored to be the chief guest in this Atal FDP program. So the topic of this this course is very timely. It is very important in the current scenario because India is working on using AI in different aspects, becoming AI enabled in different aspects of life, particularly in digital health. And this particular workshop pertains to that. Today, you have AI apps which can explain in very simple terms if a patient submits a medical condition. And it is all possible in today's scenario, given the huge development that everybody, including India, has been making. For that, you need good training mechanism, first of all, because that is the part where the AI system or the open AI systems work. If the training is inappropriate, then the system will not function in the proper way. So the training has to be on proper, reliable data. And this data, particularly in medical research, we have the data from the world, but not much of data which is specific to the Indian population because our genetic build is different from non-Indians. Let's say from for the Caucasian people or the African people or the Chinese people, we are not the same genetically. So it is very important to develop India-specific data and reliable data such that the medical facilities can be reached to the entire population all over the country, particularly since we are a huge population-based country with a lot of the population in the remote villages. So mobile applications also become very important so that it becomes accessible to the to the public of different levels, of different social and economic strata. So that is the objective of digital health, which is one of the prime focus in India's AI movement. So with that, I thank you once again, and to the organizers for organizing this particular program, which is so very timely. And it will, I do hope that the participants will benefit widely from it. Thank you so much.
Thanks a lot, ma'am. Ma'am will also be continuing her talk on the role of AI in clinical research.
So should I continue now?
Yeah, ma'am, yeah.
So do you have the PDF? I think I put it in the Google form, or I had to upload the talk, or do I share my screen? What do you prefer?
Is it possible for you to share the screen, ma'am? If not,
yeah, let me see. Let me see.
Yeah, okay.
So can you see where is my screen? This is the desktop.
Yeah. Yeah, ma'am, your screen is visible.
Okay. So can you see?
Yes, ma'am.
Yes, ma'am.
Yeah.
Yes, madam.
Yeah. Okay. So what is the time of my talk? Actually, this is a longer talk. I'll reduce it accordingly. So what is the time I have? Please let me know. So do I end at 6:30?
Just a minute, ma'am.
Let me know. Then I'll accordingly.
Yes, ma'am. Your session will be ending at 6:30, ma'am.
Okay, so we will go like this. So what is digital health, and then what is AI and learning, some brief introduction with some of the applications that we do. So digital health has got a huge diversity. It has lab tests, it deals with the proteomics aspect, imaging aspect, the mobile phone aspect, looking at the vital signs, genomics, and the devices, social media, and so on. So if you look at the emergency department, it's got limited resources, it's very much time sensitive, and it needs critical decisions. And there is huge data in the emergency department. So you have electronic records for over 3 lakhs emergency department visits. So you have the triage information of text, then maybe the comments from the expert, specialist consults, physician documentation, then these repeated vital signs, continuous values, lab results, which are continuous valued. So you see, you've got huge volume of multimodal information, which needs to be taken care of at real time. You cannot take 1 month to give a decision, because in the emergency department, it has to be arrived at immediately so that proper steps can be taken. So you have demographic data based on the age or gender, socioeconomic status, lifestyle, then the medications taken, then over time, how the patient is functioning, progressing, maybe longitudinally over 10 years, how the system is, how the treatment is progressing. Then there could be medical claims, again, based on the treatment, the insurance, then the lab tests. So all these data come in. And a part of it may be needed for a particular application. Then there is temporal modeling of disease progression. You need to find markers of disease stage and progression, statistics of what to expect when. Then estimate a patient's future disease progression, how the progress will be of the treatment, how the treatment is progressing, whether any change has to be taken or not. Now, mobile devices therefore become very important, given countries like ours, where we have a huge population and most of it is focused in the remote villages. So mobile devices started with laptops and PDAs. Then netbooks became an inexpensive option. Then tablets, smartphones, and mobile devices have emerged on the market. Then these apps have come up, mobile health applications. They have had a huge impact in healthcare because now you can, in fact, send the ASHA workers to the villages, remote villages, and they can take some, if they have the app, they can take up the inputs and propagate it, transmit it to the experts in the bigger hospitals in the cities. Now, the smartphone revolution actually is underhyped. More people have access to phones than access to running water. That is typically in India, maybe they don't have access to toilets, but they have access to multiple mobile phones. So we've never had anything like this before since the beginning of the planet. So what is this mobile health application? It is the delivery of healthcare services via mobile communication devices. To improve the delivery of healthcare, to improve quality and access, care coordination, lower rehospitalizations, improve outcomes, lower the infection rates, monitor the patient status in real time. So many of these are unrealized possibilities. The types of these mobile health technology could be tablets, smartphones, apps, wearables, implantables. Tablets, they maximize portable technology in the patient encounter. You have point of care documentation, real-time care coordination, labs and imaging, patient education, therapy benefits, access to past medical history, countless additional benefits. So this is how a tab can work in the hospital also. Smartphones, these are ubiquitous in healthcare for care coordination, external device connection for testing and diagnostics, let's say for blood pressure monitoring, blood glucose levels monitoring, and using the smart apps. So these are ways in which the mobile devices can be used. These apps have a wide range in scope, online apps or on a device, health and wellness monitoring, diagnostic and testing monitoring, patient education, labs and imaging, social media integration. So these are the different aspects where these health apps can work, and they're used all over the world now. Wearables, they are most popular in the personal fitness space. You do some workout, you want to find out how much calories you have spent or what is your heart rate and how good is your heart functioning. You have them on your watch also. So you track and trend the activity levels, sense and analyze information from substance emitted from transdermal source, use social media to enhance user accountability. That is also peer pressure effect. So these are some applications where they're used. You can wear them in many places. Implantables. Implantables have been around but are being redefined. So possible vision correction and enhancement, vital sign or blood glucose monitoring. You put in something which is of the size of a code button and you can hold a smartphone and get the continuous glucose monitoring. So these are implantables. Relay information back to nurse, case managers or physicians. So if you have an implantable, then that information can be going back to a specialist sitting in the city, maybe. So remote inputs can be taken. Lots of diagnostic and monitoring potential. So these are some of the wireless implantable medical devices. So as a part of a technology thing, technology is not the panacea for the healthcare industry, but it is part of the solution. Is there any question? Somebody has put up a hand. So with that, let's move to AI. So AI is a program that can sense, reason, act, and adapt. Machine learning is a subset of that. So these are algorithms whose performance improve as they are exposed to more data over time. And deep learning is a subset of machine learning in which multi-layered neural networks learn from vast amounts of data. Now, deep learning and machine learning is shallow learning. Deep learning is the bottom row. So in machine learning, you need an expert to give you some handcrafted features. You have to extract the features and feed it to the classifier. That is the traditional pattern recognition since late 1950s. So you have to extract some features and you need an expert in between, which is expensive and time consuming. In deep learning, it's done automatically. It's got a trainable feature extractor and a trainable classifier. It's also called end-to-end learning, and it's fed to the classifier. So this is a conventional neural network, multi-layer perceptron, which is machine learning, shallow learning. When you convert it to deep learning, this is how it looks like, convolutional neural network. So you see how complicated, how much more complicated it has become. Therefore, you need much more data to train. And you need very high performance computing like GPUs to train deep models. Now, shallow versus deep learning, as I said, in shallow learning, you need handcrafted features. You require considerable engineering skill and expertise. Whereas the key advantage of deep learning lies in automatically learning the features, extracting the features. Now, why in medicine? Because you've got imperfect knowledge in medicine. There could be incomplete understanding of the biological mechanisms, imprecise test measurements, uncertainty of normal ranges of test results, simultaneous presence of multiple diseases, missing information. So you need some kind of intelligent learning or analysis, automated analysis, interactive learning or active learning. So there are different aspects to digital health in the terms of the medical data. You can have images, you can have genomic information, histopathological information, and many more. So radiomics, radiogenomics, and personalized medicine. Radiomics is an overlap between machine learning and deep learning, computer vision, and medical image processing and analysis. Personalized medicine is about offering the right drug to the right disease at the right time with the right dosage. Now, what happens is based on suppose you have the same group of patients with the same diagnosis and same prescription for a particular set of symptoms, based on the genetic information, the diagnosis or the impact of that treatment or medicine would be different. So for one subgroup, the drug could be toxic and not beneficial. For this, the drug could be toxic but beneficial. Drug is not toxic but not beneficial. And this is the best option where the drug is not toxic and beneficial. Histopathology is a diagnosis based on visual examination of tissue sections under a microscope. It is still the gold standard in cancer diagnosis, for example, in grading of cancer. Now, with the growing number of digitally scanned tissue slide images, computer-based segmentation and classification is a high demand area. Automated grading is important, but it is challenging because of the huge volume of data. There are many other challenges, like you see, this is a histopathology, a slide image. And if you expand this particular yellow square, you get more resolution. Again, resolving further, you get this. So as you resolve more to higher resolution, you get more information, but you need more computer memory and computer performance also, which is a huge computational burden. Moreover, different pathological labs use different kinds of colors, and the images become different. Here you see it's blurred. Here there is a tissue is some kind of damage is there, tissue tear, and this is tissue folding, and this is the staining effect. So all these affect what the computer diagnose. And then the example of color variation as seen in different pathological labs. Although this is the same image, but you see for a computer, it becomes very difficult to distinguish between them. Therefore, you need some kind of active or interactive learning. So this is one of the research we did on prostate cancer histopathology images. So this is how the ISUP grading is done. So this is the whole slide image, and you take patches from there. And based on the patches, we fed it to a deep network, which was the efficient net here. And then we use this kind of a framework to arrive at a decision about the diagnosis. Some other applications that we did was segmentation and survival prediction in brain tumor and detection of diabetic retinopathy from retinal fundus images. So here are two kinds of brain tumor images. This is the high grade and this is the low grade. Low grade obviously has better prognosis. The patient survives longer, while high grade has poorer prognosis, patient dies. It's very dangerous. Now, to the naked human eye, you see it's very difficult to distinguish between the two. Therefore, AI becomes very important. So we participated in a challenge in MICCAI, and we got a good position. So this is the UNet, which typically is used for segmentation, but we modified it to take care of the spatial information which was lost in normal UNet. So what we designed was the multiplanar spatial convnet. So there was a novel spatial max pooling layer which passed the maximum locations to be subsequently used during the unpooling operation. So this is how the tumor looked like and the different parts of the tumor in the different sequences of the MRI, T1C, T2, and FLAIR. And the segmentation error around the boundary that had to be solved, and the false positive. So these were the two aspects we needed to solve. So we passed the maximum location along with the other information, and we used three two-dimensional multiplanar representations, and we use the consensus function to combine them. And class imbalance was a major problem that had to be handled. So we modified the loss function accordingly. And in the leaderboard score, we find that our group had this red is the top score, and with compared to other teams from around the world, our team came up with very good results. Then there was the overall survival prediction problem, where we use machine learning because the number of data was small. So we use the radiomic features, which are as follows: the first order gray level statistic, shape, gray level co-occurrence matrix, gray level run length matrix. And these are some of the qualitative results and quantitative results of segmentation and survival prediction. And finally, we talk about the diabetic retinopathy. Now, diabetic retinopathy is a very wide problem all over the country because India is the diabetes capital of the world. And in this work, we have collaboration with the Sankara Nethralaya and Dr. Mohan's institute in Chennai. So diabetic retinopathy, these slides, the basic medical slides are from my collaborators. So diabetic retinopathy is of two kinds, and it is very important to screen it very early, because if you can detect it early, then you can cure it or hold it there. It is an irreversible process. So if you are unable to detect it, it causes permanent blindness. So this non-proliferative diabetic retinopathy, it has 3 stages: mild, moderate, and severe. It's better to catch it here other than in this part where it is proliferative and the eye is severely damaged. And there it is just permanent blindness. So it is always very useful to, therefore mobile applications become very useful, so that the villagers can be, the image of the eye can be taken in mobile apps, let's say by the ASHA workers, and transmitted to the ophthalmologists in the cities. So the tragedy is that only 5 to 10% of the diabetic retinopathy is sight threatening and is referable to ophthalmologist for further management. But unfortunately, the village people, they don't want to go to the doctor. They think it is cataract, they think it is eyesight problem, power, when diabetes has possibly attacked them and diabetic retinopathy has occurred. So it's very, very important to track these remote village population. That's why mobile app and digital health is very important. And 90 to 95% of the diabetic retinopathy management is possible by good systematic control. A multifactorial approach of targeting sugar control is of hyperglycemia, blood pressure, dyslipidemia, along with lifestyle changes. Now, the tragedy is that 90% of the vision loss due to diabetic retinopathy is preventable by early detection and timely treatment of the sight-threatening DR. And all individuals with diabetes require regular and repetitive annual retinal screening. The difficulty of the problem in India is that there are about 22,000 ophthalmologists in India, but over 74 million people with diabetes to be screened annually. So automated approach becomes very important, involving a computer-based analysis of the fundus images, so that the burden of the health system in screening for diabetic retinopathy can be reduced. So this was what we did actually. So there were different pathologies which form in the fundus image. So these are like microaneurysms, hemorrhage, soft exudate, hard exudate, and depending on the density of the occurrence on the retina and how many, there are 4 quadrants in the circular eye. So how many of the quadrants are affected, that determines the grade of the diabetic retinopathy. So these are some of the outputs we have. I'm not going into the results. And then today, digital twin is also very much used. It is a virtual representation of an object or system designed to reflect a physical object accurately. It spans the object's life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to help make decisions. So you see, in digital twin, you can work on the digital version of the twin, not on the real brain. Let's say you are doing brain operation. So you can do whatever you want to do on the digital version, digital twin, instead of harming the real brain. And once you have decided what you have to do, you can work on the actual place. So that is the advantage. So with that, I end. Thank you. If you have any questions, I'll be happy to answer.
If anyone is having any questions, please post it in the chat box. We will read it to the ma'am.
I have to stop sharing. From where do I stop sharing?
Ma'am, it's already stopped.
Okay.
Yeah.
Okay. So then it's okay. It's over then.
Yeah, ma'am. We're just waiting. If anyone is having any query,
Okay.
they will be able to ask you. I repeat once again, if anyone is having any queries, please post it in the chat box.
They are sending direct messages. Why don't you put it in the general place?
Oh,
It's difficult to read all these. They were
that's
asking
fine.
about the slides. They were posted in the Google form. So I think they will share. And AI will assist the doctor, not replace the doctor. Why don't they put it in the to you? They are putting it directly to me.
Yeah, ma'am, I'll change the settings so that they will put it to me.
Yeah.
Yeah.
Participants, we request you to post your queries to the organizing committee.
Ma'am, we have a question here.
Yeah.
What type of features are to be extracted to detect diabetic retinopathy?
So deep learning will automatically detect. You don't need to detect. If it's machine learning, you have to consult with the doctor and then get it. Deep learning will just get the training based on the images, and the images the doctor needs to mark out the region. Then the machine will be trained. That is called annotation.
Ma'am, we have another question over here. What are the challenges in applying AI, ML, and deep learning in cataract surgeries?
What? Please repeat.
What are the challenges in applying AI, ML, and deep learning in cataract surgeries?
It's I mean, cataract surgery is that is what the doctor will do. That the AI will maybe use a robot to do it. That is more of mechanical aspects. Yeah, AI will guide the robot to do the cataract surgery if the doctor cannot do it, or the doctor can operate on using some AI. AI will suggest the strategy how to do, but ultimately it is the specialist who has to take the decision. The machine can't do it everything on its own. The machine is not replacing the doctor. Machine is helping the doctor. You don't think that, I mean, anybody won't go to a machine for a decision. Everybody will like to go to a human being.
Ma'am, we have another question over here. Is there any way we can detect what features that the deep learning architecture is extracting?
What? Please repeat.
Is there any way we can detect what features that the deep learning architecture
There
is
is
extracting?
this explainability, interpretability of the deep learning. That is also a very important aspect of the research. So they're trying to analyze what kind of features are being extracted. So you can use heat maps, visualization tools to see what all features are getting extracted. That way it is useful if you get a meaning, because then the doctor also understands what the machine is doing.
Okay. And then how do we learn basics of modifying or customizing the deep learning model?
That depends on the problem. You have to train and do experiments, and you have to design your own model, modify it according to your problem. You need a lot of data, and you need a lot of time to train it, and you need high performance computing. Otherwise, there's no point saying that I'm doing deep learning with 10 data. That's meaningless. That's just what going to the waste paper basket.
Okay. And then how do we select appropriate images out of tens of images of each patient?
So you have to look at it carefully. You have to sit with the doctor or the doctor's assistant. So you have to see which are meaningful. The doctor will be able to say, or the radiologist or the pathologist or whoever, how they do, that is how the machine should be trained to do. They know which all images are not good. So you should, who is somebody who is not a doctor cannot take that decision. You have to have a doctor if you want to do medical research. And the doctor will tell you which are the useful images. So you need to have lot of such useful images, otherwise you cannot do deep learning. Just as a doctor has to learn when the doctor is a student from the books or from the experiments, doctor learns to become a doctor. So the deep learning method also has to learn to become an expert. Without learning, it's not possible.
And then how do we, sorry, I already read that, ma'am. Is there any minimum limit on the number of images for deep learning? Also, if there are less than 1,000 images, which machine learning is preferred?
You cannot say like that generally, which machine learning is preferred. Depends on the problem. You need to talk with your teacher or supervisor. You cannot say generally like that. Some based on this application, what is your application, what is the kind of data you're looking at, depends on that. And if today you can generate data also, so you need to have a lot of data. There are generative algorithms, generative AI, generating data.
And then do we have any approved medical database in India that is public or can be obtained on demand? If not, how might a clinical research get started?
You have to collaborate with some doctors. So actually you have publicly available databases, which are mostly of the Western people. And you can work on those publicly available databases, which are free. Otherwise, everything is under not free. Or so if somebody has a private database, you need to request that person if they are willing to share. Otherwise, you need to set up a collaboration with a medical institute and take their data. So that is the most difficult part.
And ma'am, how can we improve the quality of images if we have low quality images in deep learning?
So you can have other good images also. Don't take the bad images. If a human being cannot detect from that, how do you expect a machine to detect? Machine cannot be better than a human being. Only because so much data human being cannot process so fast. Otherwise, the power of human brain is much more. So what a human being cannot do not expect a machine to do.
Ma'am, and then which deep learning algorithm is best suitable for segmentation?
There's nothing called best. So the basic was UNet. After that, so many people have come up with so many other models, designing. So, and today you have these transformers also, vision transformers, then foundation models. So many things have come up. There's nothing called best. It's you need to have it efficient. You need to have it low cost. Today, the focus is on green technology. That means it should consume less power and it should be efficient. It should work faster. So that is more important.
Ma'am, and then there's this one last question. Is there any framework for image dataset creation in health sector in India, especially for researchers? Any guidelines to follow when image data is to be collected from the hospital?
So the hospital, you need to have a collaboration with the hospital, and you need to talk to the doctor because it is based on the hospital records. There is privacy issue, ethical issue. It's not such a simple problem because a patient may not be willing to share the data, hard data. So you need to take consent in the hospital and then the all those particular personal information have to be removed at the hospital end, like the name and age and all those things. You should not be able to access that particular person. So all these are ethical issues, privacy issues, which the hospital takes care of. So you need to have a collaboration. I mean, as a computer science person, you cannot do it.
Thank you, ma'am. Thank you for patiently answering all the questions. And also thank you for your valuable insights on AI's transformative impact in clinical research.
Thank you. Thank you.
Thank you.
Yeah.
So further moving on into session 1, Future of Computer Vision in Medical Field by Dr. Ganapathy Krishnamurthy Sir, Professor at IIT Madras. Sir has over 25 years of research experience who specializes in medical imaging, multimodal preclinical imaging systems, and AI-driven diagnostic solutions. He has led pioneering research in automated disease detection, deep learning powered radiological assessments, and AI-based low-cost imaging solutions. His contributions in fluorescence imaging, micro-CT scan systems, and in vivo imaging for disease models have been widely recognized. He is the recipient of the MICAI ACDC Diagnostic Challenge Award at 2017 and the ISBI Longitudinal MS Lesion Segmentation Challenge Award at 2015. His work in collaborating with radiologists for AI-based medical decision-making has significantly advanced diagnostic accuracy in clinical settings. His research team has developed advanced AI frameworks that enhance diagnostic efficiency and medical imaging interpretation. His projects also focus on low-cost imaging solutions, making AI-driven medical analysis more accessible worldwide. Over to you, sir.
Hi, thank you. Thanks for the introduction. So let me start. What happened? The screen went away. Should I share my screen? Is that what I'm supposed to do?
Yeah, sir.
Okay, I'll try to see what I can do. Okay. Because here is, I don't know whether it can share. Hold on. Okay, thank you. Slides as background. Wow. Okay. Okay, there no other way other than sharing the entire screen? Just 1 second. Sorry. I've been.
No problem, sir.
My talk is not that long, so I'm assuming I should be able to do this. So I made something current. Got it. Can you see it?
Yeah, sir. Your screen is visible.
Okay, all right. So I'm just doing a slideshow. Okay, so thank you so much. So my talk is titled Medical Imaging in the LLMA. So I think the previous speaker was also worked on the same, at least some of her work seems to have been in the same area. I just joined towards the end of the talk. So I'm glad that I didn't include a lot of my things because that'll be very similar in terms of, AI and radiology, but I'm just going to give you a slightly more what I might call a hand-waving look into different things that are possible now with AI, and what can we do, what will the future hold, right? So that's what we want. So some of the stuff I'm going to show you right now might be, I think a lot of people out there know more about what I'm going to show right now than what I do personally. But this is all work done by the students in my lab in collaboration with in the first case with radiologist, actually MD PhD student from Sri Ramchandra Medical College and research institution, and all the other work is done in collaboration with my PhD students who done very well. Okay, so they are the ones who even helped me put this together. So I just the broad outlines is what I will talk about. Okay, so this is again a summary of about 2 or 3 publications in scientific reports. This is work. All of this work is on Indian data, so that's a good thing. I'll also point out some drawbacks with this data. So and then we'll go on to a more modern technique. So this is basically radiomics. Right? That's what. So this is where we are going to start. So because I do this first, I look back at radiomics. Does not imply radiomics is no longer useful. The idea behind using any kind of ML or AI or even conventional compute in radiology or in medicine is to actually solve the problem. So it doesn't really matter. It doesn't have to be AI. Just one. That's what I wanted to do. Emphasize. So radiomics is pretty decent. In radiomics, confluence with just routine. I shouldn't say routine. In conventional ML algorithms, I can actually give good results. Okay. So lung cancer is what we worked on. It's again one of the most common and deadliest type of cancer worldwide, as you all know, because of widespread air pollution, widespread smoking, of course, genetic causes also. I really don't know the contribution to each one of them, but I think smoking is in the top 10 or something like that, right? But what is important is to differentiate between benign and malignant pulmonary nodules, right? And once they are caught early, it seems that the patient might have a slightly better chance of survival. Okay. And so because if it progresses, then the chance of survival, like in brain tumors, it's not very good, right? Prognosis is not very good. So the objective of the first study was to predict whether given pulmonary nodules are benign or malignant, right? So, so one of the first things to do here is to actually do a preliminary exploratory data analysis, which we did. I'm not going to walk through all of this, but this is a very rich data set. The number of patients is small, but we have a variety of age groups. Again, this is a retrospective study, right? So it's not like we recruited patients for this. This is again hospital data, and these are the for instance, this is the age distribution right there. This is a type of lung tumors, and one big advantage of this data set is that this has been verified using histopathology, right? So they've done a biopsy and confirmed whether it's a tumor or not. The disadvantage of this data set is that it's not done for every tumor in a lung, because many of the patients will have multiple lesions in the lung or nodules, and it's not possible to do a biopsy on all of them. So one per patient has been verified, and that's the one we focused on, right? And this plot shows the different case distribution of benign and malignant nodules. So the data set is sparse. And the one other small drawback is that the size of the lung nodules is also not big. So typically, I think if you look at this Luna and various other publicly available, mostly from the US data sets on lung nodules, I think they are slightly larger nodules. I think greater than 3 millimeter, etc. Right? So this is slightly smaller nodule. So the disadvantage of that is when we tried to use, so this is because we only had, I think, 88 patients or less. We thought we would train a neural network on the open source data or freely available data, and then use that to segment the nodules here. But it turns out it didn't transfer well. So even with some fine tuning, it wasn't working at all. It was kind of disappointing. Maybe we made some mistake in the processing. But still, that goes to show that, if you do train with open source data, which is great that they are making it available, but if the data doesn't originate in India, it's quite possible you won't generalize that well. Of course, it's always necessary to add local data to it at the hospital level, at least. If you can't make it public or you can't get it from some other place, if you are affiliated with some hospital, you should definitely try to use the data that is available at that hospital. So at least the idea is to use it at least in your clinical setting. So it should work that way. So we had to do some tricks here to get this to work. But I'm going to present only the radiomics results, and we're not exactly focusing on lung nodule segmentation. So there's plenty of literature on it, all kinds of neural networks, especially CNNs, to actually segment lung nodules. All right. Okay. How do I go to the next slide? Okay. So this is just shows you the distribution of data. We have 1,000 scans were reviewed. So we eventually ended up with like 88, because they had the clinicians had a lot of criteria to reject. One of them being that they needed to have actual validation of whether a nodule is benign or malignant. That is only obtainable with biopsy. Okay. these are high resolution scans, right? So many of these lung nodule cases were verified by 3 radiologists. Okay. And we did use some publicly available open source ITK Snap software to do some using that whatever they had to in there to segment it. Okay. So it's not like we wrote our own. It was not necessary. The idea what we are trying to do is to see if radiomics would work. Okay. So that's the whole idea, right? And then, so we can do multiple ways of classifying. Okay, we can do classification from radiomic features, and do that. You extract radiomic features and then use many of these algorithms, SVM, MLP, XGBoost, etc. Or we can use some sort of deep learning based classifications, CT scans. So wide variety of and architectures are available. Vision transfer being one of them. Okay. So these are the different things. So when we use this deep learning data, it was actually performance was bad. That's not because networks weren't good enough. We didn't have enough data. Okay, there are a lot of issues there because every patient had a lot of nodules, right? And so we couldn't label all of them. There's not enough people to do it. And we tried labeling with some texts that were trained and all that, but their accuracy was poor. So eventually these results are not very indicative of the performance of these networks on very accurately labeled data. So just to show you that if you don't label data properly or if you don't have enough data, you can use all the networks in the world, you won't get anything. So most of the success of these neural networks, especially CNNs or vision-based models in medical image diagnosis are based on high volume of very accurately curated and labeled. When I say curated, right, it's very important. So this is again curated data, but when you look at the ones that are out there, which again, it's great that they are available. Of course, no progress is possible with those data sets, but you'll be very careful to extrapolate from those data sets, right? Because they have been like beaten to death. They have removed all kinds of outliers. They made sure that, the resolution is uniform. They made sure that, they're balanced classes. They have made sure that it's obtained from multiple sources so that your network generalizes, etc. So all of those have been, taken care of, and that's hidden from you typically when you use them. It's important to pay attention to that. So as you can see, I'm not talking too much about the architectures themselves. It's now a commodity pretty much, so it doesn't really matter. Just if you hold on for 1 second, I have a small interruption here. Sorry about that. People walking around. There are also, differences, right? In the data sets, right? If you are looking at shift in distribution for one feature correlation between two data sets. So there's a lot of difference between what is the medical decathlon data, which is like 10 different types of data sets for segmentation and other tasks. So our data set is qualitatively different and quantitatively different, right? So it's important to understand that we cannot use the same network. So it means there's a distribution shift. Whatever you train on with open source might not work. So you need collect a lot of data. So that's an important lesson here. So once again, we just extracted a bunch of radiomic features. I think that's the previous Dr. Mitra actually showed a lot of them. I think I have this somewhere in the slides. But without going into too much detail, decision tree worked, which is actually I didn't think it was going to work. And I'm surprised that AdaBoost, if you look at the accuracy, was poor. I thought it worked much better. We didn't realize it. But then XGBoost really worked. Okay. This is again, we extracted radiomics features, again, PyRadiomics, PyRadiomics. As we use standard software, we didn't change anything. So 90% accuracy, right? But then you compare it to like some previous studies. Again, these comparisons are very qualitative. It doesn't mean that previous study was bad. So we really don't know many of the small things, details they would have changed, etc. So it's not a very good way to compare, especially since the data sets for these things is not easily available, right? So what is the advantage of using these radiomic features, right? This is one big advantage, which is the interpretability. Like, so if you use radiomic features, right, you can actually know what those numbers are, right? You can actually say, okay, what does this number mean, etc., which is a huge advantage, especially if you are trying to do something clinically, right? On the other hand, if you're using deep neural networks, it's an issue that you cannot, interpretability at this point is not there. Like, right, what exactly do those weights mean? Or what exactly do those feature maps mean is something that is not possible to explain at this time, given the rate of developments, right? For the next slide. Okay, so then, so the conclusion, right? So radiomics improves classification accuracy when data set is small. Remember, we're trying to differentiate between benign and malignant data sets, right? And interpretability is good because it aligns with visual cues and morphological characteristics, right? So it's a very low cost system. All of the software is free and it's not very computationally intensive. Many of those algorithms run on CPUs. It's very nice, right? So that's one advantage of using this. So this is the past kind of, this is where things were, and it's not bad. So if you are able to properly do this, you can use it for a variety of applications in a clinical setting, because one thing is that you can actually explain what those features are, and you can actually say, okay, based on what was the decision based on, even if you are using these as an assist, right? So radiologists can definitely, use these kind of systems, and there are many commercially available, or you can develop one on your own to make this work. Okay, so we go down the chain a bit. So we can also do a lot of other problems, right? So for instance, you can look at benign, malignant, and in malignant, okay, are they primary malignancies or they metastasized, right? And then if they are primary malignancies, then are there two different types? Are they adenocarcinomas or squamous cell carcinomas? As you can see, with the limited data set, we didn't have too many things to work with. But then it's a very this is an important classification: adenocarcinoma versus squamous cell. Also, again, primary versus metastasis is also another classification which is important, because all of them determine the kind of treatment you want to give, right? You want to treat the primary cancer if you have metastasis, and if it's primary malignant, you want to see whether it's adenocarcinoma or squamous cell, because apparently they do respond to different drug cocktails, okay? Which I'm not an expert in, but this is again information gleaned from talking to people in the clinic, as well as the radiologists mostly, who told me that this was a important thing to do. Okay, so we can just drill down on a particular problem like this. So we had, with our limited data, we did, and with collaborate. Of course, this lot of the work is done by the MD PhD student. So she's also a radiologist, and she's finishing her PhD up as we speak. These are publications related to her work, so I'll give her some credit, quite a bit of credit, in fact, and the team that worked with her, right? So so these two, this classification again can also be attempted. So we did attempt it using again radiomic features to see whether such things are possible, right? So and it did, right? So splitting malignant nodules from, then again, there's one of the things that we did, right? So there are some malignant nodules, and among malignant nodules also, there are some COVID nodules, right? That's also another thing that we did. So how can we, distinguish between malignant and COVID nodules? Similarly, malignant between adeno and squamous cells. So MLP actually worked well. So once again, these are things that we have to investigate further. Why did MLP work better now compared to XGBoost or anything else? It's very difficult to explain at this time. But as the number of data sets increase, then I guess we can safely use a neural network to do these classifications, right? Okay, so this is again, I just want to end here in terms of the, what do you call, the previous generation of work. So, but then when I say previous generation, it's actually complete work. A lot of the, radiomics features have been identified, and they've been used for, even for breast cancer classification, benign versus malignant. In this case, we have tested it on figuring it out with difference between adeno and squamous cell carcinomas, as well as benign and malignant carcinomas, right? Benign and malignant nodules. So this is like the previous generation of quote unquote, AI, if you want to call it, wherein, extracted features. In this case, they are fairly automated extraction of features, coupled with some powerful machine learning algorithms with boosting, etc., gives you a fairly good guideline. It can it can assist the radiologist to make a recommendation, which can be further taken up by the person who's going to treat them, like the oncologist, right, etc. So this is the previous generation, right? The next generation we're going to talk about now AI, right? In the sense, what we now call AI, basically deep neural networks. Most of the time, I mean, except for the last few years, where vision transformers seem to have emerged as a a network of choice. Except for the last few years, convolutional neural networks have been the workhorse of this vision problems, right? Especially solving any vision problem, pretty much, you use the CNNs. In fact, a few years ago, if you went to any conference, it is basically CNN for X, right? CNN to solve any problem X, whether it's medical imaging or conventional computer vision, right? So that's where it was. But one of the important problems, and I'm not going any of the things that you typically would be expecting. And I think that those solutions are like out there everywhere, right? And explanations, etc., are very nicely written explanation blogs, etc., about how these networks are used in medical image problems, right? So, for instance, before I go any further, I'm just going to make a small note about that. The idea is like so. What people usually use CNNs for in the beginning was to do image segmentation, right? Can you segment the heart? Left ventricular segmentation? Can you segment brain tumors? Can you segment liver tumors? Can you segment the bone, the vertebrae, all of these, right? But these are not, I mean, it's not like it's a thankless task, or useless in any way, but these are tasks that are typically done by a radiology technician at a console, and it took forever. But then if you're going to do a lot of patients in a day, especially in India, that's going to be the norm. These techniques can help to speed up the process. So once you have the segmentation, then you calculate some quantitative feature values, and based on that, you make some recommendations. So for instance, if you're doing it for cardiac MRI, you would calculate the ejection fraction, the size of the left ventricle, size of the left atrium, right atrium, myocardial wall thickness, all of those things you would compute. And these have standard measurements. And if they are not within the standard measurements, then you can make the radiologist can make some recommendations, right, to the cardiologist, right? That's the idea. So now, so those are, one class of problems, right? So, and of course, the second class of problems is diagnosis, right? Automated diagnosis. So typically in a, what do you call a screening setting, right? So you do chest X-rays to screen for TB, and also for diagnosis, let's say pneumonia or COVID, etc. That is basically the input is an image, output is a classification or a category. And that's true for breast cancer, even for lung nodule, lung CT, you can do it as a screening tool to see, somebody has some symptoms, then you refer to the CT scan and they can see if he has any malignant nodule. So those are some of the common applications. So I'm just going to talk about something slightly different. I mean, this is again not uncommon, but super resolution medical imaging is something that is catching on. And here too, idea is to transform low quality scans into high precision insights. So this is very important too, right? Because this is a useful thing to have. People all over the world are working on it, is because hardware is expensive. So if you want to buy the latest MRI, it's going to set you back by like, I don't know, $1 million or something. Even the CTs are like that. So can you get more bang for the buck from a low-end hardware? That's what this is all about. And it's a very exciting field to work on also. It's a non-trivial problem to solve. Not that the others are trivial, but this is generally non-trivial to solve. And so because your output is, if not as big as your input, is bigger than your input, right? And we're talking about input sizes of 256 cube. It's large volumes, and you want to have even higher volumes as output. So that's a challenging task and very, very impactful, right? So it improves diagnosis. So you're not trying to automate the diagnosis per se by doing some kind of detection of nodules, etc., but rather present a much, much more refined picture to the radiologist or whoever it is that is looking at it, so that they can make an informed diagnosis. So I'm going to talk about, this is something we are doing some work. So I'm not presenting that, just presenting a couple of approaches. They're fairly straightforward, but just to show you the power of these techniques. So this is modern AI, if you want to call it, that is where AI, that is ML, where these deep learning algorithms are being used in such kind of not so common tasks that you would think of, right? So this is one other aspect of it. I'll just mention in passing as we move to the last section of my talk later on. Okay. So the idea is higher resolution, right? How to obtain higher resolution, right? So typically, if you want to get high res, right, there are several ways to do it. Even with the older scanner, right? You can, for instance, if you have only 16 slices, you can change the pitch You can do a helical scan with a pitch which is half the length of your detector thickness. But then what you do, and you also increase the energy or increase the tube current. If you're doing CT, you can increase the tube current so that you get more statistics. Therefore, much higher quality image. SNR is very high, but that increases then the dose to the patient. Right? And if you're going to do MR, then you scan for a longer time. That will also give you better results. Okay, but all of this come at a cost, right? If you're increasing the scan time, you can just, all you do is you also increase the chance of motion artifacts, and sometimes you just need this in a hurry, so it's not possible, right? So SuperS algorithms there play a huge role. And if you take a regular image, okay, and convert it into a high-res image, that's what we are looking at. And if you look at the bottom panel here, high-res, this is the ground truth. You can call it the leftmost is the ground truth. Then you kind of figure out a way to lower the image quality by blurring or subsampling. And then this is the input to the algorithm, and the output is a super resolution image. So if you look at this, this is actually a generative model, and what it generates is high quality data from low quality data. Okay, so that's what we want. So this is a generative model. This is one of the generative models. So you're all familiar, those who have done some courses in deep learning, etc., or have used it or are using it. You will know that these are one. You all know one, at least one generative model, especially for generating images, that is GANs, right? And now more recently, diffusion models. So these two are again good candidates to try and solve this problem, right? So we're going to look at a couple of these things. Okay, so this one is called DiskDiff. Okay, and the idea behind this thing is to improve the quality of low resolution MRI scans by leveraging complementary information from. So you have multiple contrasts. So if you look at this, there are multiple. Once again, let's not go into too much detail, right? But the idea is there are multiple information here, and you use that to get a very high resolution image of one type of image, right? So so the idea is this is a diffusion model. So there are multiple inputs. All those inputs are used to eventually predict a noise that you subtract from, and you get the output corresponding to a high-res image. So let me quickly, and SE is the squeeze excitation module. We will again, all of these are well documented in literature. I would really urge for you to go and look through it, right? So the idea is the following. The diffusion process, that's how it works. You start with the high-res image, okay? And then you start with an image and you progressively noise it, okay? So the forward diffusion, which is like from left to right, processes Q perturbs HR, the high resolution MRI X, by gradually adding noise, right? The backward diffusion process denoises the perturbed MRI, conditioning on its corresponding low res version. So you need to start with the noise, but then you have a, why it conditioned on it? Because you need to know, you have to generate a specific structure, not some any MR structure, but the specific structure specific to that person, right? But an MRI conditioning on its corresponding low res version Y and other available MRI contrast. So it is just not, so the denoising, so the forward process is deterministic, right? So you start with a high res image, keep adding noise till you're left with only nothing but the noise distribution. But when you go back, you predict the noise to be subtracted in every step. So if you take 10 steps to get this noise image, you go back 10 steps. On each step, you predict what noise is to be subtracted. But that is done by a neural network, right? And that neural network takes as conditioning input not only the low-res image, but also other information that can be obtained. Like for instance, if you're doing multimodality imaging, that is, different scan sequences for the same patient, you can use the other scan sequences as input also to get you a very high quality reconstruction of the high res, right? So this is again a diffusion model based. So it's a generative model. So diffusion model, that's how they work. So the idea is you start with an image, you add noise to it incrementally in steps till the whole image washes out. And then you come back towards the image by using a neural network to predict the noise added at each step and subsequently subtracting. Okay. Now it's a very easily said thing, but there is a lot of theory behind it. We don't go into it. But the idea is if you keep subtracting, then at some point you'll get a high-res image, right? But then the idea is, you can't get any high-res image. So you have to condition your neural network that predicts the noise at each step so that you can subtract using available information, which is in this case, your low-res image, okay? So it's a very, very, powerful paradigm. And I urge all of you to try it if you're ever going to work on some. So it can be used for many problems, okay? So just look up the literature, very, very good, descriptions on how a generative model like a diffusion model can be used in this context. For instance, low res to high res, segmentation, all kinds of things, right? But of course, you have to decide where to use what. So for these kind of tasks, diffusion models are really good, where you're actually doing a generative task, right? But if you want to do segmentation and all that, I don't know, you have to think about whether it makes sense to do this, right? So that's the idea. Okay, so these are some results, right? They're able to get from here, you get this, and then you back to super res, right? So you can actually, you have to look up this paper to see if those results match. So my students put it in there because we also tried some experiments in our lab to see what kind of networks are useful. So then this could be one of the results also, right? But you see there's some washout here, right? This is the actual image. Some texture is lost. So, okay, so we can't really blame that, right? There is something called SUBGAN, okay? Super resolution using GANs, right? So here it's basically 2D. You use 2D. That is aims to generate high resolution thin slice images from existing low res thick slice images. So for instance, okay, so this is another thing. So when I talk about it, so the biggest problem in medical imaging is when you have thick slices. So the axial is pretty much uniform in many cases, but it's only the z-axis resolution which is bad, because if you want to get noiseless or fairly noise-free images, you have to average over a thick slice, both in MR and CT. So the advantages of the advantage there is, since you are averaging over a thicker slice, you will finish the imaging faster, because if you do thin slice, then in order to cover the entire volume, you have to do a lot more scanning, especially for MRI, right? So one of the tricks they do here is that they did not use the inherent 3D nature of the data. Okay, what they did was treating the volumetric data as a series of 2D slices and applying super resolution process to each slice, while maintaining some coherence across slices to ensure that the 3D volume is consistent, right? So you can't, if you independently generate 2D slices, then you have all these artifacts. When you look them up at the coronal, so if you're generating axial slices independently, and if you look at the coronal and sagittal section, it will be jagged, some kind of error will be there, right? So it's conditioned on, so one way is to make sure that your input has two or nearby slices, etc., right? And another trick I think is that you have a 3D patch also. So for instance, what you can do is you can actually do it in multiple planes also. That's another thing, right? So you can do multiple planes. You can use neighborhood. If for one slice, you can do the slice before or slice after also as the input, so that you condition on that, right? So that's the idea. So let me just 1 second. Again, pardon the interruptions, and suddenly people want to talk to me after 7 p.m. Okay, that's fine. So the idea is, yeah, so you can use these tricks again to go from low res to high res. There are lots of work in this area people have done over the last few years. It's a very rich field, once again, to explore. It's a kind of a non-conventional use of these deep learning networks. Once again, a very powerful application. So there are multitude of papers for all the other things, right? If you want to do image segmentation, even registration too. I don't know whether you looked it up. There's a lot of neural networks that are good for registration also. So you can definitely try that also, right? Especially for brain. That's where a lot of the applications arise. It is again the results of thick slice cubic interpolation and super resolution interpolation. Okay. So now these are again slightly more recent past. So we had radiomic features, very powerful features. I talked about radiomic features because they are very powerful and they've been proven in many applications. Of course, you can also do anatomy-based features to do some things, but typically radiomic features are the ones people use. And then followed by, the advances in deep learning, wherein people are using vision transformers, CNNs, deep CNNs for doing 3D processing of data, medical imaging data, and you can use both either 3D or 2.5D or 2D processing to do a lot of the tasks in the radiologist workflow, right? So that'll be huge gain. Now, what we're going to look at is what is the next step? What are people working on? Like, this is kind of current, straddling the current and maybe the near future, the foundation model paradigm, right? So the idea is to pre-train at scale and fine-tune at the edge. And I'm sure most of you would have seen this also, right? This is where it's going, right? So the advantage is that the foundation models are pre-trained on massive data sets, right? And you adapt them to specific tasks, right? So the one advantage of this, especially in medical imaging, is there are lots of conditions which are not very which are very rare. So if you do an imaging of that, right, it's not going to get you much data. Like, you have to wait for like 2-3 years before you get like 100 samples or maybe even just couple of 100 samples, right? That's the idea. So, so once again, there are multiple advantages here. You can actually pre-train on any kind of data, natural images, and then maybe adapt it to medical domain, right? And it also minimizes the need for extensive expert notation in many cases, right? So the idea is if you're going to develop something very rapidly, this is a very good model in the sense you use an existing foundation model. Right? Or if you're so inclined, if you have the resources, you can develop one yourself. Okay. So, and then you can use it downstream for downstream tasks very easily. So this is the advantages that are provided by foundation models. Again, these foundation models, not necessarily just LLMs, right? Foundation models are there, or the one I'm going to show you, you should all be familiar with. But there are foundation models for specific domains, right? So you can train foundation models for specific domains and then use them for small problems for which data sets, or even for more common problems for which data sets are hard to get, right? So, if it's very difficult to do a clinical study for let's say a prospective study to collect 10,000 data points, right? It's going to take forever, and all the bureaucratic overheads are large, but you can do a small clinical study. It's not too hard at your hospital level, etc. And a very few data sets, people don't mind also annotating them, etc. So those sparse data sets that you have, you can annotate very, very carefully so that, you can use them to fine tune these foundational models, right? So let's look at what is there. So we have used one of these models called, and everybody can do this. Okay, so we used for speeding up brain lesion segmentation, right? So once again, this is overlap with the previous speaker. That's okay because I'm going to talk about the aspects that Dr. Mitra had discussed. So I'm just going to give you an example of where these things are useful, right? So the idea is the traditional challenge is insufficient expert level data, which is true. Like even though there are now countless open source data sets, freely available data sets, not in numbers or few, right? Maybe except for chest X-ray, etc., you have a lot. But for if you look at CT data or MR data, it's not much, right? You have like maybe, if you collect every here and there, maybe 1,000 volumes, right? That will not be enough, right? So the segment anything model from Meta is one of those foundational models, which has been trained on medical imaging also, but also on all kinds of other data. So it basically, has a wide variety of data sets being used here. I think I don't remember exact number, but it's a very large number, but they're not necessarily all of them are what you call medical data sets. So that's the advantage of these foundation models. You just train them with pretty much what you get your hands on, and then you can use that later, right? So it's pre-trained on mask pre-training, right? So 11 billion images and 1 billion masks, right? Transforms segmentation approach, right? So no need for CNN VAT development from scratch. So if you want to do segmentation with this, you have to develop this method from scratch, right? You can use visual prompts for guidance. This helps radiologists work with the model interactively. So this model can take as input a prompt. So all of you are using LLMs will know that if you want to do as LLM to do something for you, let's say ChatGPT or any of the other things such as DeepSeek, whatever, you just have to give a prompt. So even if you have the problem, you have to add some extra information to it so that that lets the LLM solve the problem or answer your question appropriately. So in that case, here you can use visual prompts like points, bounding boxes, etc. So this can be an interactive tool for the radiologist. So you don't have to really sit down and draw some exact contours, but rather provide foreground, background, etc. Right? So can be fine-tuned for medical image analysis, such as in models like MedSam. So MedSam is a derivative of SAM, where they took that SAM model with weights and they fine-tuned it on a lot of open source medical imaging data, right? And it's a lot of the data used to training this SAM is basically natural images, but it works very well for medical images. Also, I'm going to show you some examples. So, for instance, you can do positive, negative sampling. Like these red stars indicate that it's not tumor, and then you can put something which says it is tumor. So you do an inside-outside prompting, right? Points from eye tracking. You can track eyes. So this is something work in progress in my lab. You can track eye movement, okay, and use those eye movement. Like if you gaze at some points for too long, that gets a higher weightage, so on and so forth. That can be used for prompting. So one cool application was, also provide bounding boxes, right? And automatically, so if you put a bounding box around this, it automatically segments the eyeballs. So these are the eyeballs actually, and they segments it, right? Also used for brain tumor segmentation of brain tumor. Of course, it doesn't do the compartments, just give you the gross tumor volume, right? But it's an interactive tool, and the training is pretty much minimal. There's absolutely no training, just click and it's done, right? So that's one of the things that you can, right? So the process is, how do you get those prompts then, right? So what are you going to do then if you don't, every time somebody has to draw a box? But there are lots of times when the radiologists themselves will look and, make some markings on the image. You can use that as prompts for this particular algorithm, right? And so it leverages existing clinical workflow. So radiologist is going to look at the picture, at the image, and is going to make some markings on it. You use that to do whatever task that is required, in this case, segmentation, right? So all kinds of things are possible. So again, this is one such application. So we did it on 1 and 2 brain lesion images, pretty decent, 0.88, okay. MedSam showed clinical tune where it showed similar results. I think there was an older version we tried. The newer one's probably better. They have retrained it and it's now very good, right? At this point, it was zero training. This is just like doctor going and click, done, right? So that's the huge advantage, right? So that's what you want. And that's typically what, and it gives you, it gives the radiologist a lot of time and very quick, you can just, if the results are not satisfactory, you can do further prompting. And instead of just sitting there and exactly tracing contours, you get this done very quickly, and also to the satisfaction of everyone involved, because it's not some unknown thing doing it. So you can actually explain what you did. And you can also say that, yeah, I'm satisfied with the tumor boundaries, etc. So that, there's not a lot of problems regarding interpretability, etc. Even though this is a deep learning based neural network, right? So from here, where do we go, right? The generalist model. So these are specific foundation models. We know generalist model, right? And what is the generalist model? It's multimodality. So this is the next, again, this SAM is slightly in the past, actually. So the field is moving so fast that within every year or 19 months, 18 months, you have phenomenal turnarounds, right? So multimodality imaging, right? So why work with just images, right? Why not have also, so for instance, there's a report, there's a reference report, right? Usually a patient is referred to a scanner, or, or some oncologist would refer for a scan. And then they would say in that, like, we think the patient has not exactly this language, but, in whatever the language that is clinically used, as to, okay, this patient might have such and such condition or showing such and such symptoms, and therefore we want to do an MRI or a CT. And then when the CT is done, this text report can also be as input, because then there is an association between what is there in the text and also the anatomy, right? So that's where the multimodality aspect is very useful. So to use these models is also now catching on. Once again, there are lots of these models. Okay, I'm not going to go in training. There are many models which are now trained with, for instance, MedGemini is trained with text, 2D, 3D images, gene expression. I'm not an expert in gene expression, etc., genomic data, but you can also any kind of data that you have, right? And then once you have it, and the output is also like varied, right? You can use it for classification, question answering, report generation, risk prediction, all of these things. But that's because you are able to give us input after transforming. Of course, the major trick or major important thing behind these models is that you have an embedding of all your data in some common domain. And in that common domain, all of them are aligned. Therefore, they can be used for any downstream task as one particular type of embeddings, right? So lots of them, MedPalm, Biomed GPT, BioGPT, I think Lava, all kinds, they're called vision language models, hybrid models. So huge, some of these are not open sourced. You might have to, I think, MedPalm, MedGemini, or kind of, you have to like write to them and they will share it with you and you can definitely use it. I'm not sure whether they let you fine tune it, they might, but you have to use the cloud. So, and if you have your own data, that might be a problem if you don't want to share it on the cloud. But there are quite a few things out there that you should definitely try. The advantage here, so what is the approach here? The approach here is that let's not restrict ourselves. So this is basically AI in medicine, right? It's not AI for X, or it is not deep learning for imaging. So far, I've only talked about imaging, but these models, as they are called, they're hybrid models that they can take anything as in. And advantage with that is then the patient is, you see, there are many aspects, right? See, for instance, the patient is not just coming to you once. It's not the first hospital visit of the patient. This is not the first time the patient is getting an imaging or some test. There is a history of data. So that's all input, and that actually improves your, whether it improves segmentation or registration, that's one question. And one thing is whether it helps improve diagnosis is another question, right? So definitely this is where a lot of the focus is on. If you are a hospital with a lot of data, you should try out some of these things and see whether, and in fact, right now it's easier more than ever to actually fiddle with this, work with these models and see how they can be, used for your kind of data, right? The last one, kind of, the future of AI, if you want right now, what everybody is looking at is the sense of what is very exciting, where is this all going to, right? Then I say, are we done? Like we have now very good models for pretty much. SAM is an excellent model. There's other models also which give you good representations, that is good embeddings of any data, and you can use those embeddings on any downstream task using some typical machine learning algorithm, right? So that's there. But then is that sort of problem solved? No. You go to next level. I think is that's what we looked at, is not to just restrict ourselves to images, but also to any kind of data. So now once that is there, then what else is there, right? So these are called agentic workflows, right? So the agentic workflows are what is the next step. That is basically the core is you just allow your AI to actually automatically, so what do you call, what is the word for it? Let's say I said automatically, but on its own, without any guidance, do a particular task. So think of it, you have a workstation, like a PACS ready workstation. You send in a cardiac MRI, okay, latest sequence, you got a latest machine. Immediately there is an agent. Agent is basically, this is a software or a program that reads in the image, okay, and there it calls these segmentation tools, it calls these LLMs, etc., to identify what that image is. Says, oh, it's a cardiac image, looks at, then of course looks at the patient report, and based on that does the appropriate processing. Now the processing is of course done by particular algorithms you have developed for each of them, right? But then the agent autonomously decides. So this is the word, autonomous agents, which decides what to do, and it's given tools. So far we look at all of the deep learning algorithms. This is, you have to give them some input, it will do something, right? Input and output are defined. Here it's slightly open-ended. You have an AI which is typically an LLM, which is looking for some requests or query from you, and based on that query decides on course of action. Okay, so that's a very important thing. So for instance, hey, so you have a chest X-ray, I want to find out regions of high lung opacity, right? That's what you are looking at, especially in the left lung. So then that's an LLM listening to your prompt. That's your visual, that's either a audio prompt or a text prompt. Then based on that, the LLM decides whether to call the segmentation routine or the classification machine. So no, you want to look at left lung, and you're looking for regions of high opacity. So it decides to call or quote unquote run a model which does lung segmentation on chest radiographs, figures out where the left lung is, finds out regions of high opacity there, and presents the list to you. And then you say, okay, this looks bad. What kind of diagnosis do you have? Then the agent parses your query, which is basically an LLM running, right? So one of the things is a LLM, right? And then there's a memory system. Basically, this keeps track of all your requests in the short term, and there's one more memory which keeps a long term for a particular action, right? And the action framework is tool use. Tool use is basically either calling other programs, calling other deep learning models, etc. The last time when you ask, okay, what do you think this is? It calls a classification model for chest X-rays and gives you something. And you wanted to make some observations, then it has another report generating AI that will take the images as input and the classification as input and generates a report. So all of these are there. So basically the key capabilities are natural language understanding, which is provided by LLMs, which general you have to do so-called chain of thought prompting to decompose your whatever you said into small steps. Select the appropriate tools and execute them. So this entire package is an agent, right? So for instance, you have a docs agent, right? So basically, this is if you ask a question, it will figure out appropriate document to fetch from a certain vector database. So what would that be, right? So if there's a radiologist who is curious, oh, I want to find out what was the written on this particular patient's report when he came here 1 week ago. Then there's a gender database of reports that you have, vector database, you go through, find out where the patient is, and maybe also retrieve similar patients, so on and so forth. So all of these are possibility, and these are done by agents. In the sense, you don't have to specify every step, rather act like you're talking to another medical professional. So this is a huge advantage on top of what you have. So these sit on top of everything. So basically, the agents are those which orchestrate all of the other algorithms you have seen overviewed so far. That is the large language model, multimodal models, just deep learning models, etc. Right? So that's what agents do, right? So, but again, the more ambitious thing again outlined by some companies is that it basically does everything. So, patient walks in. So as soon as a patient walks in, you have a system that takes in the patient's history, etc., and then triages the patient, right? Very quickly, whether he has to go see he or she has to go which specialist, does she have to go to the imaging room, so on and so forth, right? So, and also prepare documentation, generate documentation, which can be used by the healthcare professional who's going to look at them. So all of these, and of course, protocol suggestions for imaging. Of course, all of them will have will have an oversight by a doctor, but then not from scratch, right? So there'll be, maybe you can ask the agent to do multiple suggestions, and doctor can quickly decide, okay, based on what is there in the reports, quickly decide whether to accept these suggestions or not, in a way that so that the decision making in the end lies with the doctor, right? That the thing is that the idea is just to reduce the time spent by the patient in some mundane administrative tasks, okay, that take up time, right? So in the end, post-visit report generation, follow-up scheduling, etc., all of these things can be orchestrated by agents. So it's not something that just you're not really just looking at. So this is again a slightly bigger, what do you call it, zoomed out view. The thing is that it is not just about, okay, this chest X-ray cancer or not. It's totally the patient journey through the hospital can be orchestrated by agents with the oversight of healthcare professional. That's the entire idea. Okay. So enhanced clinical decision making, reduced load on doctors doing administrative tasks. So many repetitive tasks are removed. So basically, administrative burden is what it is, and then hopefully it will improve patient. Of course, it will, because wait time of the patient is reduced. Generally, can be able to see more patients, and therefore it's much more pleasant experience overall. Okay. So that's the end of my talk. I kind of finished earlier than I because I told them that I'll do only 45 minutes to 1 hour, but it gives me time to ask questions, and any other details you want, I may try to give. So that's the end of my talk. So to summarize, there is an entire gamut of applications that can be done with this with the current developments in AI. You can use somebody is scribbling on the screen, I think it's not me. So which includes, for instance, starting from very conventional radiomics analysis for specific cases, more general processing, for instance, more generic applications, and then you talk about AI used for pretty much handling any kind of data, to AI used for in the form of agents, autonomous agents, for the entire patient journey in his visit to the hospital. Okay. So thank you very much. That's all I have to say regarding this future of AI or deep learning in medicine. So any questions I will take. Thank you so much.
Thank you, sir. So we have some questions. I'll read it out to you.
Fine.
Is it possible to segment honeycombing pattern from lungs detection of pulmonary fibrosis? If so, what method will give good results?
So I haven't seen those images, so it's very difficult to suggest anything. But again, if there is a very significant density difference, lot of the common, you go look up OpenCV and see whether any thresholding algorithm might work. If there is not, but there's only slight textural difference, if you have enough data, you can train. There are a lot of pre-trained networks out there trained on lung data, you can use them to fine tune and do it. So, but I don't know how much data is available, what these things look like. This is if it's 3D, it's going to be different, right? But again, if the density difference is huge, try OpenCV first and then see how it works out. Region growing, etc. might work. Yeah.
Okay. So there's another question. Can we identify the tumor CT scan and normal CT scan without lab datasets with the help of CT image only?
The question is not very clear. In the sense, if the patient doesn't have a tumor or not, right? In the sense, okay.
Yes, sir. Not without the actual lab datasets, just with images there.
You can train anomaly detectors. If the tumor is fairly big and it's only 1 or 2, you can train anomaly detection in images. So you just look them up. So anomaly detection can be used in this process. So if there is, basically there you train the network to only work with. So you don't need, well, for testing you do, but the training can be accomplished with just plain normal data. So you don't need tumor data. So for instance, one of the work we had done in the past is train an autoencoder to reconstruct, or even a GANs like the BAE to reconstruct your input slice, right? Now you train those at the slice level or patch level with only non-tumor slices. So the once you train the autoencoder well enough, when a tumor slice comes in, the reconstruction error will be very high. So that's a difference. So that way, yes. So, in a nutshell, anomaly detection, yeah, possible.
Yes, sir. There's another question that is there any freely available datasets combining brain imaging, genetic and clinical assessments for schizophrenia or neurological disorders?
Oh, there is one. Cancer imaging archive is there, but it's not for neurological diseases, though. That's a very good question. Brain imaging for neurological disorders, I have not seen. I'm sure there is something for Alzheimer's, dementia, and all that. But any other outside of that, I don't know. I don't know the exact what do you call that when I found it. Like you can find it. You can just Kaggle is a good source of such data sets. Okay. There is a website for biomedical grand challenges. You can just look them up. Okay. They have a list of every grand challenge data out there. So you just Google biomedical grand challenge, it will take you to the page. There is a while ago, I landed into this website called Mindboggle. That has only brain data. So you might find whatever you're looking for there. Possibly, yeah.
Thank you, sir. And which techniques can be used for improving the low quality X-ray images in deep learning?
Okay, so there are multiple angles here. Low quality in X-ray, again, it's a 2D image. So there are two aspects here that you have to please look through them. One is the super resolution thing I talked about. So there will be, you can train a super resolution network on top of the chest X-rays. There's another one, because if it's done with a low dose and if you have a very poor detector as well as a very old X-ray tube, then there is also noise. A slightly different problem. So you get this, one of the ways to do is you have to look at denoising networks. So there are networks for denoising, the networks for super res. So so you have to do a combination of these two to get there. If you are going to use neural network, simple thing is if it's just noise, there are lots of these conventional denoising algorithms. So non-local means is a very good algorithm. You can try it. It removes noise very well. Okay, so that's the first step. So try the conventional thing because you don't have to train anything. It just removes the noise. Super res, again, networks are available, but you still have to fine tune with your data. Otherwise, it won't work.
Okay, sir. And for beginners, which model to start with and which data set should be used?
Okay, so this is a difficult question. Like I said, SAM, start with SAM. The SAM weights are available. Segment anything model is very good. And then you can fine tune. They even give you a notebook to fine tune. So don't waste too much time. Unless you are thinking, okay, let me tell you this. Unless you are very specific about in terms of like, I have only like this small laptop and I want the model to run on that laptop, right? And unless you have something like that, if you have some problem like that, then it's better you can actually distill SAM. So distillation is there. Actually distill SAM into a smaller model, quantize it, run it on your handheld or your old laptop on the CPU for the inference, right? Otherwise, you best to work on this large models with pre-trained weights and fine-tune on your data. One advantage with that is it's the reason I'm suggesting this, very emphatically because the data requirements reduce, right? That's the idea, right? You can, I think, I don't know, there have been studies, but I'm not very sure which to recommend. So for instance, two choices. One is you start with your own model, train your own model from scratch. But maybe you have lots of data, then you can train your model from scratch. Is that better than fine tuning on a foundational model? This is a difficult question to answer. Like, I don't have an answer to that question. On the other hand, from the sheer convenience point of view, like it's already there, it's been trained on a lot of data. Use it, you will get very good results. And if you're not satisfied with the results, then you think about maybe you had some weird application. I want it on my cell phone or on my iPad and all that. That's it. Then you have to do some extra work. But that also you can just do distillation. That works too. So that's my suggestion is go with some very large foundation models that you can fit in your computer. Of course, if you have models like, for instance, these LLM kind of models at full, you can't run them on, you need a server, right? That's not possible. But many of the vision models are small ones available. Use whatever is there. That's not a problem. Okay.
The next question is, how agentic AI play a role in healthcare industry?
I just explained it towards the end. I mean, again, at this point, it's just people are just talking in the air, right? So their idea is to, see, typically agentic means it's an autonomous agent which does what humans do. In the sense, when you walk in, somebody asks you who are you trying to meet, what is your ailment, what specialist you want to meet, especially in the hospital. Instead of that, you just maybe talk to a screen or something and it just directs you. Okay. So so the agentic AI workflow can be anywhere in the hospital. Like the entire hospital can be done. But again, there are some security concerns, etc. Because many of these agents hallucinate. That's a problem. So under certain constraints, for instance, very simple thing is you have them in a processing workstation in the context of what we talked so far. So you have an image processing workstation. All you have to do is just send the image along with the report. So the agent is basically something that orchestrates between different models. So the LLM will read the report. A very large foundational model will read the image. The outcomes will be then combined with another LLM or model, and the outputs can be displayed on the screen. So there is no human intervention. So like I said, this is basically autonomous, right? So that's the idea. I think I've chosen my avatar to be very bad. So I get two horns on my head. I'm trying to get rid of it. Let me see. I didn't realize. Okay.
Oh, so that's
Okay, now it's better. My hair is like that. Okay, all right. Very nice. Okay, sorry. So yes, so that's the idea, right? So you can have it anywhere. It depends on application. So idea is just, it's a very broad answer. You can use it anywhere, and also if you if you think of hospital, I mean, there are people there, I'm sure, who know more about the hospital workflow than I do. There is a certain stages that a patient goes through, right? Whether the patient is hospitalized or if it's outpatient, right? They have several stages, like they have to go register, then they have to go see the doctor. Doctor does a consultant. Doctor says, okay, go do this scan. Then you go do the scan. When the scan is done, scan is read and get given back to the doctor. Then you come back to the doctor, speak to him, etc. In all these steps, there are a lot of humans involved. In many of those places, can you replace with the agent, which kind of speeds up the process? That's the idea.
okay, sir. So the next question is, what kind of features can be used for COVID detection?
I don't actually have an answer to that. Okay. There are lots of papers out there. So that's the reason why I didn't talk about these things. Right? It's just, so my suggestion is to just go read whatever literature you can for COVID-19 detection. There are plenty of resources out there which talk about this. I personally don't recall any of them. I think the previous speaker, the professor, showed some many huge list of radiomics features that are used. Maybe you can borrow our slides. Those are typically the features that I recognize some of them, right? Histogram of gradients. You have your noise standard deviation, etc. So those are very standard features in pyradiomics. That's what people use. You can code yours outside of that. It's just going to be more work. That's all. Okay.
So they're asking about the visualization tools for machine learning and deep learning models to suggest you in.
Actually, it's a good question. That's a good point. Visualization tools. So someone, in the sense of you want to look at the feature maps, is that something, or you're going to look at, both PyTorch and Keras, they have their internal tools which lets you look at what the network structure is. So you can just list the layers, weights, etc. That's one thing. But if you want to visualize features, you have to write your own code. I mean, to pick out the feature maps and put them on the screen. That's also there, fairly automated. Outside of that, I don't have a good. There is one tool. I hope I'm remember this correctly. It's called Orange. Orange, okay. But it's more like a tutorial thing, but please use it. It lets you visualize many things. Let me know if I answer that question, if you use that tool, and let me know that. Okay. I'll get back to you. Okay. That's my answer. Yeah.
Can you please suggest any research ideas related to vein disease except Alzheimer disease?
Brain disease except Alzheimer's. There's plenty.
Vein, sir.
Huh? Vein.
Vein disease. Yes, sir.
Veins, the blood vessels, right? That's what you talk.
Yes,
Veins.
sir. Yes.
No, veins. There are lots of things. I mean, I don't know. I actually am not a doctor, so I'm not familiar with many diseases. But see, the point is, it's not. This is something you have to decide. See, one thing I won't give you what vein disease is, but let me suggest something. Right, there are two extremes you can adopt. Okay, one is go do a less studied disease. That's a rare disease. Whatever it is there, that's a very good, because nobody will be working on it. So you are fairly certain anything you do there, you go there, do some thresholding there, that will work. People will be very happy. You have something for a very rare disease. That's one end of the spectrum. The other one is do something which is very high incidence. Lots of people have it. Okay. That's another disease that you can work on, right? So that's the only hint I can give. I don't know the exact disease, but if you're asking me what I would work on, I would work on something which is very hard, which is like a rare disease, or very high impact, but maybe not so hard, but very high impact, because it affects a lot of people. So you figure out some solution addressing some part of that problem, that will work. So those are the two suggestions I have. I don't know exact disease names. I'm sorry, I'm not that knowledgeable about those things. Yeah, you have to forgive me for that. Yeah, please.
Sir, a participant asked if you could share the Indian dataset you worked with. They
Ah.
assured proper citation and request.
Definitely, it's not meant to share. So anyway, I will say yes. But it is so we will be publishing it. So please look out for it. That time you can download it. You don't have to ask us either. So at that time it will be out there. Okay. So I've been pressurizing a lot of the hospitals to to at least 10, 20 data sets you can put out there so that people can use it with appropriate clearance, everything, right? So you can even find the patient and talk to them, convince them that retrospective study, and 10, 20 at a time we can, because there's not enough, right? But we will share it. It's not like close to, that's one of I've been pushing for it, right? So right now it's not in that space, but once they publish, we're trying to publish it in a journal which publishes data sets. So it will be made accessible as part of the publication. So not a problem. Definitely, yes. Please look out for the publication. Yeah.
Yes, sir.
It's in the
Sir,
work.
and
I'll submit it. Yeah.
okay, sir. Yeah. And another participant asked that she's trying to work on lichen planus and sclerosis, but couldn't get more data on it. So she's asking if you could suggest
What
any.
multi-MS, sir? Multiple sclerosis.
No, sir. She just mentioned sclerosis. I
That's
don't
my.
know.
I'm
I'll
assuming
ask her.
MS. MS, there's plenty of data out there. MS data is there. I don't know of any other sclerosis, but this one is very common. People work on it. There's one person who was. Do we have any? There's plenty of questions. That is public. Hey, so there's one person who asked about any approved medical database in India that is public, or there are a lot of people that are messaging me directly, I think. That's a bad idea. We need to message the coordinator. She can help you. Yes, but this is a good question. They are in progress. So multiple government bodies are setting up, trying to curate, and it will soon be available, hopefully in time for you to use. I don't know how long it will take. Many of these things take time. But yeah, it's in the works, in the sense that people are actually trying to collect it. So it's not like nobody's doing it. There are Tamil Nadu has made doctors, and there are quite a few consortiums which are doing this. Right? Just that advertisement is not big, right? But you have to look. It's there. But in any case, central government has initiated a couple of schemes. One of them is to collect such large data sets. It'll come through. Yes. Segmentation, can you suggest medical imaging? Hey, so some general questions. Inside with concern work the Indian identity data set. Yes. Where to download data set? This is biomedical grand challenges in biomedical imaging. Just Google it. There's a website. It'll take you to pretty much every database under the sun. Kaggle. So another data set, right? Kaggle is one. These two places are where you can go find data sets. That's all I can say. NIH has a giant database. You have to find out, but you have to get their permission to take it. So you need some ID, etc., and they'll let you download it. They have even genome data. So that's amazing actually for thousands of patients. Yeah. Anything else?
They've asked if there is any tool for federated learning.
Oh, there is. I don't recall. So this is not something I carry in my head. There
Okay,
is.
that's fine.
So there are frameworks. So federated learning frameworks are available. So it's there. You do have to look for it. So please, so I give you one suggestion. Okay, I'm sorry I'm not able to recall exact things at this time, but if you do, please send me a consolidated list where people are asking for very specific things, and I will respond them to, like, in the sense like where is this, for instance, this Alzheimer's data set or vein disease and all that. I can ask someone and we can pass the
Sure,
information
sir.
on to you. Yeah. So that's
Sure, sir.
I don't have I only remember stuff that I work on, so I don't. The exact details I don't know, recall.
Okay, sir. We'll do that instead.
Yeah, that's the easier thing to do. But my suggestion is, why don't you just use Perplexity? You all know Perplexity? Perplexity.ai. Go there, it's free. Use the free version. It's pretty good. And just a very good search. Okay. Ask same question you ask, it will give you answers. Okay. This is pretty good actually. Not DeepSeek or ChatGPT or anything. Google AI Studio can also go out there. Google has its own deep research that you can try that too. Perplexity.ai has very nice stuff. You just go there and give a prompt. It searches the web, gives you very nice results. So if you have very specific query, like what is this vein related disease, sclerosis data set, location, etc., some very specific like that, please ask. Right. Arrhythmia disease detection with advanced transformers can we incorporate? What kind of data is this? Are you looking at ECG or images? So I'm not sure. So ECG. Again, this is a very well studied. Right? We got like Apple Watch doing it, right? That's where level it's commoditized at this point. But again, not everything, all the not questions have been answered. There are startups which tell you that they can do 100 diseases with ECG, etc. You don't have to use transformers. I mean, I don't know whether transformers are the best. There's a recent paper which showed that transformers. So I'll just let you know what this is. So as far as tabular data is concerned, time series data is concerned, LSTMs, RNNs, and even these autoregressive models can beat transformers cheaply. Okay, so only recently for tabular data, I think there's a tab something transformer which showed better results on time series data or even tabular data, not even time series. I don't know about that, right? So so that's the suggestion I would give you is to try, don't go with transformers right away, but try more conventional techniques because they generally outperform transformers on many tasks, especially in time series analysis. So far as I know. There have been recent developments in transformers where they would have beaten it, but then you're going to get very good 90 more than 90% for cheap, why not, right? So many questions about XAI. Explainable AI is good. You should work on it. This is again, it's very useful in a clinical setting because it gives more confidence to the people using it. Hepatitis, I don't understand the question. Please type complete sentences. Yes. Okay. Are there any more questions that are done? Hepatitis B related data, but this is what liver imaging. What are you going to? What is? Look, I'm not a doctor, so you have to tell me exactly what data you're referring to, right? So I know some tests, I know some data sets, but I don't know everything. So when you say hepatitis B, are you looking at blood tests, any kind of other kind of, or you're looking at liver imaging, or any other kind of images, images which are related to symptoms? You have to answer that, otherwise I can't help you, right? Glaucoma, where will you get more data? You have to go talk to your local ophthalmologist. There is nowhere else. Okay. Yeah, so that's the only thing. So all eye-related diseases, there's plenty of data sets out there. If you just you use Google search, right? That's it will give you. Yeah. Okay. Okay.
Yes, I hope everyone's queries being posted and we sir helped us with it. So Thank you, sir,
Thank you.
for your enlightening session on AI-driven computer vision in medical applications.
Thank you. Thank you very
Thank
much.
you, sir.
Okay, okay. Bye-bye.
Thank you, sir. Moving on to session 2, Clinical Image Features in Object Recognition by Dr. S. Sumitra ma'am, who is an associate professor at the Indian Institute of Space Science and Technology, Thiruvananthapuram. She holds a PhD in machine learning from the Department of Automatic Control and Systems Engineering at the University of Sheffield, UK. She completed her MTech in Computer and Information Science and her MSc in Mathematics from Cochin University of Science and Technology, India. Her professional journey is enriched with international research experiences, including contributions as a researcher at the Center of Environmental Implications of Nanotechnology, University of California, US, and the Terry Fox Laboratory at the British Columbia Cancer Research Center in Vancouver, Canada. Her research focuses on machine learning algorithm development and its real-world applications, with her current interests spanning brain-computer interfaces, deep learning, and kernel methods. We are deeply honored to have you with us, ma'am. We eagerly look forward to gain insights from your vast experience. Over to ma'am.
Okay, thank you for the introduction. You can hear me, right?
Yes, ma'am.
Okay, so I'll share my slides first. Okay. So is it visible? Is it visible?
No, ma'am.
It's not visible?
No, ma'am. It's not visible, ma'am. You can see your screen now, ma'am.
Okay, can you see it now?
Yes, ma'am.
It's okay. So, very good evening to all of you. So, the topic given to me is clinical image features and object recognition. Okay, thank you for the nice introduction. As told, as ma'am specified in the introduction, I have worked with this medical data. As part of my postdoctoral study, I did analysis on arthritis data. And then I worked for some time at Cancer Research Center, Vancouver. There I dealt with this telomere data, right? And currently we are looking into this brain-computer interface. But I was not sure, right, what to select it as the topic is given as, right, clinical image features and object recognition, right? So I thought of introducing a algorithm for this one, right, to selecting the dimensionality of the features. Is that fine? Right. So all of you are aware of this principal component. Can you hear me?
Yeah, ma'am, you're audible.
Okay. All of you are aware of principal component analysis, right? Am I right?
Yeah, ma'am.
Okay. Right. So what is it is using for? Right. We want to reduce the dimension of the data, right? So I thought that, to quickly look it into the the mathematics behind this PCA and what is happening in the PCA and what is PCA is about, right? PC is a very old technique, but still it is very relevant and it is highly used for this dimensionality reduction. But most of those use some tools like write some PCA tools and do the dimensionality reduction without knowing the mathematics behind that. So I thought that I would introduce the mathematics behind the PCA, right? So as I said that, right, it is the dimensionality reduction method to reduce the number of attributes in the data, right? So why we are interested in this dimensionality reduction, right? First of all, that it improves it will give you good computational efficiency. It remove redundant attributes. So these are some of the good things that led us to use these dimensionality reduction methods, right? In the while dealing with this medical image data, right? The problem with this medical data is it will be very small in size, right? It will be, we don't get very big data usually, because for example, to study the arthritis data, when we collect the arthritis data, most generally these patients may be very old. They may be suffering from a number of diseases. So we need to, we cannot exclude, we cannot include all types of patients in our study, right? Because they may be suffering from other diseases, so that may affect our study, right? So usually, generally, this medical data is very small. It is very difficult to get good data, right? But their dimension may be very large, right? Usually the number of data points may be very less, but their dimension may be very large, right? So this feature, dimensionality reduction methods is very much required, right? To efficiently apply the classifications or regression methods. It is always good to reduce the dimension, right? Another case is that, for example, in the study of this arthritis data, we collect this electromyographic patterns from leg muscles, right? So we are interested to know that which muscle, is behind that is causing the arthritis, right? Uh, uh, First of all, we want to know that whether EEG patterns can be used for for arthritis detection. Second is that we want to check that among all the muscles given, which muscle is most influencing the arthritis, right? So in these type of cases, right, this dimensionality reduction methods and feature selection methods play a important role, right? So it's a very important step in medical medical data analysis, right? So before applying any classification or regression algorithm, right, this one of the step is this feature selection and features. So what is the difference between feature selection and feature extraction, right? Uh, Maybe the attributes, right? You know that attributes, right? A1, A2, A3, right? So A4. There are 4 attributes for this data, right? They're X1, X2, X3, and they have 4 attributes. Or Xi is in R4. Its length is, there are 4 attributes, right? Feature selection means from among the attributes we select the best one, a subset from this one, maybe A1, A2 or A2, A3, or a subset we will select. That is, from a given set of attributes we select a subset, right? that is called feature selection. Feature extraction is something different, right? Uh, we are actually feature selection means, for example, the corresponding these values be for first data, the A, B, C, D. That is for this one, A attribute A1 values A, attribute A2 values B, attribute A3 values C, and at A4 values D. If I selected this A1 and A2 as my attributes, then X1 will have two, right, will two attributes A1 and 2, and it will take the same values A and B. That will happen in feature selection. Feature, right, extraction means, right, this data, these values will be completely changed, right? So these, it will be, we are replacing these data with a, right, with a new vector, right? It has no, we cannot find any, right? Here I selected A1, A2 as my best attributes, and it will take the value same A and B. But that is not happening in feature extraction. We construct, right? Sorry for that, right? we'll construct more different attributes. Okay. So right, and this in that one, in this feature extraction, this PC is a very old method, and it is still, it is very much right. Uh, its importance has not been diminished at all, right? So and it uses actually, right, as you know that this machine learning, right, it's a combination of mathematics, statistics, and computer science, right? Its theory is full of this mathematics and statistics, but only for implementation we use this computer science, right? There only this computer science coming into play. So to really understand what is ML, right, we should right put time to understand the mathematics behind that also, right? Just if you are if you want to do right anything good in this field, you should understand the mathematics behind these algorithms, right? Otherwise, just as an end user, you can use the tools, but if you really want to understand how this algorithm is working, how the people have formulated this algorithm, then we should understand the mathematics behind that. And this, so just right, go through this, right, this theory behind the SPCA. Maybe it's different from other talks which you have heard till now. That's right. So first one is, right, all of you know what is vector space. It makes use of the concepts of vector space, right? For example, if you have two sets, right, V1 and V2, this first one is the set of all x in Rn such that Ax is equals to 0, right? In this one, if you take two elements from this set, whether x, take two elements from this set, okay, x1 and x2, right? Then if we want to check whether it's x1 plus x2 is also in this set, right? Let us check it. That is A of, right, x1 plus x2 is equals to A of x1 plus A of x2, right? As x1 and x2 is in this V1, A of x1 is equals to 0, A of x2 is equals to 0. So both of this will become 0. Therefore, x1 plus, right, x2 is in V1. But that is not happening in V2, right? Because V2 means, right, A of x1 will become B, A of x2 will become B. Therefore, A of x1 plus x2 will become 2B. And this consists of all the sets of x in Rn such that A of x is equals to B, right? So, right. So there are some properties, right? This V1 has, which V2 does not has, right? So that is why this importance of this vector space, right? What is this vector space actually mean? Right? Um, that is the vector space, right? Over a field K is a non-empty set capital V on which there are two operations, this vector additions and scalar multiplication, right? Such that it satisfies these, right? All these properties, right? It is closed under vector addition, associative under vector additions, right? So all these properties, there are some specific properties that a vector space should satisfy. Then only we can say such a space is vector space, right? And then what is subspace? Right, subspace is a subset of a vector space, but it's subset plus it itself is a vector space, that is called a subspace, right? So I hope you know what is basis and all. Okay, so right, so actually let us start with PCA, right? What is PCA is actually, right? PCA is right, what we are actually doing in PCA, that is the question, right? You will get something, but what is that is the question, right? So okay, so for that you should know what is this projection, right? What is a projection? Okay, right? So what is this projection means, right? If I take this Rn, right? Rn is a vector space. It satisfies all the properties. And if I take a subspace of Rn, this capital Y is a subset as well as it is a subspace, right? Then I take a X in Rn, okay, any X in Rn. Okay, then projection means that element from Y, right, which is at the closest distance to X, right, that is called the right projection of X onto capital Y. The one which is at the closest distance to this is called the projection of X onto capital Y. So in PCA also, right, we are doing the same thing, right? For example, if you have a data of length 10 and if you want to reduce it to length 8, right? So we will find a proper subspace, and what we do is like this, right? This X dash is called the projection of X onto this capital Y. The what is X dash is the point which is at a closest distance to X, right? So in the same way, right, in this PCA also we are actually finding right, this projection. So let us look what is this projection, right? So let capital Y be a vector space of R raised to n, then right, then let X is in V, right? The projection of X onto Y means, right, that point from capital Y which is at a closest distance to X, right? That is called the projection, right? So if you know what is the projection, right, then using the projection we can represent this x-axis, right, y plus z, right? What is y? Y is the point which is closest to x in that space, right? And this z is the right, z is the z is in this y perp and is called the orthogonal projection of x, right? Okay, let us take an example to understand what is going on, right? Let us take R2, okay? This is R2, okay? This is, right, what is this point? This is the set of all xy such that y is equals to 0, right? And this is the line set of all, right, xy such that x is equals to 0, and we take a point 5,5, right? So what is the projection of 5,5 onto this one, right? That is the among all the points here, find the one which is closest to this 5,5, right? That is actually this 5,0, right? So I can write this 5,5 as 50 plus, right, 0,5. Right, 5,5 can write it as 50 plus 0,5, and 50 is the projection of 5,5 onto this axis. This is right. So that is the one which is closest to this, right? And if you take the inner product of this one, it will become inner product of these two numbers will become 0. So actually we are this is what is happening in this PCA, and we will so this 5,5 has two components, 50 and 0,5, but right, we will approximate this 5,5 with this 50, right? So that is what is happening in this projection. Okay, so there is a theorem called the projection theorem, right? Let capital Y be a subspace of R raised to n. Then R raised to n is equals to Y plus Y perp, right? That is this Y plus Y perp means this is the direct sum. This is right. Direct sum means if this is R raised to n, and if Y is a closed subspace of this one, right? If you take any x from Rn, right, we can represent this x as, right, Y plus Y dash, where Y is coming from this capital Y and Y dash is coming from this Y perp, right? Y perp means the set of all elements, which is right. If you take any element from this one, then if you take the inner product with this one, right, its inner product will be 0. That is Y perp. Right. So this is the right, the projection theorem, right? Right, and this is the okay, so this is the projection operator. So from P R raised to n to y, right? Okay, so the projection theorem and the projection operator. So what is happening in the PCA is, right? For example, the dimension of the data Bn, right? We want to reduce the dimension to k, right? So we want to reduce the dimension means we want to reduce the length of the data to k. So what we are doing is, right, we have to find a proper subspace of R raised to n with dimension k, right? And then we will project that data into this subspace, right? So that is what is happening in this PCA, right? So that capital Y be a subspace of R raised to capital Y be a k dimensional subspace of R raised to n, right? And let Y be the projection of x onto Y, right? So how to determine this Y, right? So that is what it is going to look at into, right? So let E1, E2 to Ek be a, right, orthonormal basis of capital Y, right? Then Y in capital Y can be represented as Y is equal to alpha 1 E1 plus, right, alpha 2 E2 plus etc. plus alpha Ek. Okay, then by projection theorem, there exists a unique Y in Y such that x is equals to Y plus Z, where Z in Y cap, and this Y can be represented as this alpha 1 E1 plus alpha 2 E2 plus etc. plus alpha k Ek plus Z. So we will approximate this x with y, right? So this question is how to find this alpha 1, alpha 2 to alpha k. Right? So and how right, these all these are orthonormal bases, right? So this EI is equals to inner product of x with alpha I, right? So this we can represent this y as sigma I is equal to 1 to k x EI. So this with respect to the spaces E1, E2 to EK, the coordinates of y are this inner product of xe1 to xek. So the new representation of x will be this one, and this norm of x minus y is called the right error or residual of the projection. Sorry, I have a throat pain. Okay. Right. So what is happening in the principal component analysis is, right, it's a unsupervised dimensionality reduction method, right, and it is a feature extraction method. The projection theorem plays a central role in the formulation of these algorithms, right, and it will find this this uncorrelated attributes, right. So there are two types of data. One is this one where there is a as you can see this type of data and right these type of data. There are two types of data, okay, and PCA can be applied only for these type of data, right? And what is happening in this one? This is a non-linear relationship, right? The data points are non-linear relationship, and here it has a linear relationship. So the PCA works fine for this, right? When the data has a linear relationship only, this PCA works fine, right? Compared to this, the one which has a non-linear relationship, right? What is happening in this one, right? So you will be given this data x1, x2 to xn, right? We want to find a suitable subspace y of Rn having dimension k less than n, right? And project the data onto onto capital Y. The question is how to find the best subspace, right? So this greater the variance of the projected data, less is the information loss due to projection, right? For example, if you look at this data, phi 3, phi 1 and phi 2, right? So this is right the set of all xy such that y is equals to 0, and this is the set of all xy such that x is equals to 0, right? So whether to choose this one or this one, right? These are this data. This is the point where y is equals to 0, and this is the point where this x is equals to 0. We need to project to this one or to this one, right? So if you can see that if you project the data to this one, everything will be projected to a single point, which is the set 5. There will be a lot of information loss. So this is not a suitable space to get projected. Right. So what is this? Right. This PCA formulation is right. The PCA reduces this dimensionality of the space in which data lies by finding the orthogonal projection of each data onto a subspace of dimension k less than n. It works on the principle of right maximum variance. That is, it is find a subspace capital S of dimension k such that the variance of the projected points is maximized, right? This would make sure that the data points get projected to different points to the maximum, right? Hence the information loss becomes minimum, right? To find okay. So what is the first step is we have to center the data, right? That is each data is xi minus x bar. That is the first step, right? So after this centering, right, this mean will become 0, right? Um, so we need to find an optimal space, right? So right. Let S1 be a subspace of Rn generated by orthonormal subspace, right? V1 in Rn. How to find the optimal S1, right? So the new coordinates of the data points after projection onto S1 is this one, right? By the virtue of the above thing, the projected points, the mean will also be 0. So the variance of the projected point will be right, will be this one, right? Okay. So right, this why we are going for this maximum variance, right? So consider the center data, that is after making the mean to be 0. Right, thus consider the projection of xi onto a space S1 spanned by V1. Right, this by the projection theorem, right? Xi is inner product of xi V1 V1 plus Z. Right, we want to choose that V1 which, right, minimizes the residual, and this is this one, right? And so this norm of xi minus xi V1 V squared is equals to this one. So if you take when we expand it, this one, so right, we want to minimize this part. So finding V1 which minimizes norm of xi minus inner product of xi V1 squared, it is equivalent to finding V1 which minimizes, right, this one. So that is the minimum square error is 1 by n this capital I into 1 to n norm of xi minus inner product of x V1 squared, right? Finding V1 which minimizes minimum square error is equivalent to find the V1 which, right, which maximizes 1 by capital N, sigma is equal to 1 to n, right? Sigma is equal to 1 to n inner product of xi V1 squared, which is the variance of the projected points, right? So maximize, so how to find the optimal V1 is, the optimal V1 is found by solving the following optimization problem, that is this maximizing I in xi transpose V1 squared subject to V1 transpose V1 is equal to 1, right? So this expression is also equivalent to maximum V1 in Rn norm of capital X V1 squared subject to V1 transpose V1 is 1. So then we will write the Lagrangian corresponding to the above maximum optimization problem, right? LV1 norm of X V1 squared minus lambda V1 transpose V1. So right. So from this, right, we will get that V1 as an eigenvector of X transpose X, right? And we get that X transpose X is the covariance matrix of data. Okay, so this X transpose X is positive semi-definite. So all the eigenvalues of X transpose X are greater than or equals to 0. So this maximizing V1 in R raised to n norm of X V1 squared is maximizing V1 in R1, V1 transpose X V1, right? From that, we will get maximum V1 in R lambda. Therefore, a norm of X V1 squared attains the maximum value when lambda is equal to lambda 1, the largest eigenvalue of X transpose X, right? That is the optimal V1 is the eigenvalue corresponding to the largest eigenvalue. So this principal eigenvector The eigenvector corresponding to the eigenvalue of largest magnitude is called the principal eigenvector. V1 is the principal eigenvector. It is called as the first principal axis of the given data. This inner product xi v1, the orthogonal projection of xi onto v1. Inner product of xi v1 is the first principal component of the data xi. Now to find the second best optimal space, let capital S2 be a subspace of Rn generated by an orthonormal subspace V2 in Rn. How to find the optimal S2, that is the optimal V2, right? So this maximum V2 norm of x V2 square subject to V2 transpose V2 is equal to 1 and V1 transpose V2 is equals to 0, then we will form the LV1 as norm of x V2 squared minus lambda V2 transpose V2 minus mu V1 transpose V2. Then we'll take the gradient with respect to V2 and then taking the gradient with respect to V1. So from that we get this V2 is the eigenvector of x transpose x corresponding to the eigenvalue lambda. So this what is the eigenvalue corresponding to V2? This is the maximum V2 in Rn, norm of x V2 squared. So this norm of x V2 squared attains the maximum value when lambda is lambda, the second largest eigenvalue of x transpose x. That is the optimal V2 is the eigenvector corresponding to the second largest eigenvalue. So the optimal vectors are the eigenvectors of x transpose x, v1, v2 to vk, corresponding to the eigenvalues lambda, lambda 2 to lambda k. Then those optimal space capital Y is constructed as the direct sum of S1 plus S2 to xk, where Si is the subspace spanned by Vi. Therefore, capital Y is spanned by this V1, V2 to Vk. The projection of Xi onto Y is in the product of x v1 v1 plus in a product of xi v2 v2 plus etc plus in a product of xi vk vk. So the new representation of xi is this one, in a product of xi v1 xi v2 to xi vk. So this the new representation of xi with respect to the k principal axis of the given data set vj kj is equal to 1 to k. Xi tilde is inner product of xi v1 xi v2 to xi vk, right? So we can write this as in a matrix notation. So we will get it as x tilde is equals to xp, where x tilde is the n cross k matrix whose ith row is xi tilde and p is the n cross k whose jth column is vj, right? So this the species input examples and the centralize the data and form the data matrix, find the leading k eigenvalues and the corresponding eigenvectors of x transpose x and form the matrix, and this x tilde is equals to xp. So I will send you the slides, the problem is my throat is not doing well, so I don't know whether my sound is also working fine. Okay, so let us. I will just generally speak about the current work I am currently doing. Okay, I now currently work in this BCI. Okay, BCI means brain computer interface. Okay, right. So this why we are interested in this BCI. Okay, and we have a BCI device in our lab. Okay, so that we will connect that BCI device to this head. Okay, right, and then we using that one we collect the brain signals. Okay, right. And this why we are interested in this, that is there may be patients, right, who cannot speak well. Okay, right. But they can think, right? I want to move the wheelchair to the left or right, right? So they can think in their mind. Okay, right. So based on their thinking, right, this the signals has to be analyzed, right? They think in their mind that they want to move this wheelchair to the left or to the right. So their signals will be will be caught by this BCI device, and then right, we have to analyze that signals, and then we can for example, we can formulate that as a 4 classification problems, that is turn the wheelchair to the left or turn the wheelchair to the right or back or front. So by analyzing that signals and depending upon that classification result, if you can with the help of a sensor, that wheelchair will be moved to the left or right. So this is one simple applications of BCI, and the other one is that, right, in the BCI data, most of them are in foreign languages. In Indian languages, this BCI data is not much available. For example, in India, there are a lot of languages, right? We have a lot of languages. There may be variations in the data from language to language, right? Our interest is that to collect these BCI data related to this Indian languages, right? So we have already collected this BCI data related to Indian languages like Marathi, Tamil, right, Oriya. So it's so much of these type of some particular words, right, related from these languages. We have already collected these data, and we have uploaded in the IEEE data repositories. The main reason is that there is not much data available in the available in the BCI data related with the Indian languages. There is not much data available. That is why we are interested in collecting these type of data, right? And it is a this BCI this data analysis, right? It is a very it is a very fast it's a very fast growing field. So those who are interested in this BCI data analysis can look into that. And this data is of this time series nature. And also it requires a lot of pre-processing also. So there are a lot of challenges ahead. But this is a very new field, this BCI data analysis, and it has lot of it has lot of applications also. Okay, right. So any questions from your side? Any questions?
Participants, kindly share your questions in the chat box. So that's the question. Which is the best DL model for feature extraction from EEG data?
Which is the EEG data, which is the best deep learning model?
Yes, ma'am. For feature extraction.
Okay. So as it is an image, is it an image? EEG data, right?
Yes, ma'am.
Okay. Oh, we can use autoencoders. You may be using that autoencoders, or variational autoencoders. Such things can be used in this type of data.
Okay, thank you. Participants, kindly message the costs if you have any queries. Don't directly contact the resource persons or ma'am. Do you have any other queries, participants? And that's a question. Can we recognize emotion of human using EEG data?
Oh, yeah, you can. Right. Emotions can be recognized.
Okay. As of now, there is no questions, I guess.
Okay. Okay then. Thank you.
Thank you. Thank you, ma'am, for this valuable session on deep learning techniques for clinical imaging.
Okay. So shall I leave?
Yes, ma'am. Thank you. Ma'am, kindly please share your PPT
Okay.
to the house. Thank you. Thank you. So participants, just to remind you, assessment test will be conducted at end of the program. Minimum 80% of attendance and 70% marks in the tests are required to obtain the certificate. As we will also be sharing the proof session recording in YouTube for monitoring the attendance, we request you to maintain minimum of 80% attendance. So as you can see in the screen, kindly provide your valuable feedback by either scanning the QR code or using the link shared in the chat. Your feedback is important to us, and attendance will be monitored based on the responses received. You'll be collecting feedbacks daily. So with that only, attendance will be monitored. We'll also share this link in the group. So kindly fill the feedback.
From here, we wrap up day 1 of our faculty development program. We extend our heartfelt gratitude to all the speakers for their insights and to our participants for their active engagement. Today's sessions provided us a strong foundation in AI-driven medical imaging and deep learning techniques, setting the stage for more advanced discussions in the coming days. We look forward to seeing you all tomorrow for another day filled with expert talks and hands-on learning. I'll remind you again, tomorrow's talks also start on 6 o'clock. So please join sharp on time. Thank you and have a great evening.